Hey guys, so now we're gonna go a little bit more in depth into determinants and inverses. Um, so just to recap, this is gonna be the second deep dive in this linear algebra series, and this one is gonna be a little bit more involved. So get ready. You might wanna bring out a pen and paper to just follow what I'm doing, but I'll try to go as simple as possible. Okay, so to recap. Whoa, where's my colors? Okay, to recap, what we did last time is we introduced this index notation, right? So we introduced this index notation. And what this basically was we split up the matrix into, we split up the matrix M. It could be an n by n rectangular matrix. We split it up into its elements, M, I, J. And I, as we said, were the rows of the matrix, and J were the columns. So for example, if we have a matrix, a 2 by 2 matrix like this would be M11, this would be M12, this would be M21, and this would be M22. And then from there, we said we can multiply matrices via index multiplication. So the ikth element of the matrix P would be the sum over some index J of, let's say, M, Ij, and Njk. This is the rule for matrix multiplication in terms of the indices. So this is multiplication rule. Okay, and then we said that we don't really need this sum because we have this dummy index, J. And so in Einstein's summation convention, we can just rewrite this guy as just Mij times Njk. Alright, that's all good. Okay, so now that we've reviewed that, let us move on to some more topics. First thing I want to talk to you about is just some general properties of matrices that we're going to need in the future. So let me just write general properties. Alright. Okay, so here's the deal. First things first, matrices are in general non-commutative. And what this means is that if I have two matrices A and B, then A times B is in general not equal to B times A. Because, well, why would they be equal to each other? Matrices are not numbers, right? So there's no reason why AB should be equal to BA. And there's actually this, there's this instrument that we use, not really an instrument, well, there's this definition. It's called the commutator of A and B. And it's written in these brackets here. So the way you would read this is that the commutator of A and B is defined to be AB minus BA. And if it's equal to 0, then we say that the two matrices commute. Alright, we're going to need this when we talk about diagonalization. Number 2, even though that in general matrices don't commute, they are associative. What associative means is that if I have three matrices A, B, and C, then A times B times C is the same as A times B times C, like that, or the same as AB first and then times C. This is all good. Those are just the properties. Another property, not really a property, but there's this thing called the transpose of a matrix. So transpose. And what the transpose does is that if we have a matrix Mij, the elements of the matrix are Mij, and the transpose of this matrix, which we write as a T on the top, all it does is that it flips the rows and the columns. So the transpose of a matrix then would be equal to Mji. You see how we flip the rows and the columns? Let me just give you a quick example of that. So let's say I have a matrix 2, 1, 2, 8. Okay? The transpose of this matrix, we flip the rows and the columns, so it would be, so the diagonals stay the same, and then the rows switch with the columns. So it would look something like that. And of course, in the index notation, it just looks like that. And one last thing I want to talk about is the trace of a matrix. So trace we write as TR, and the trace of a matrix is nothing more than the sum of the diagonal elements. So it's the sum over I of MII. Okay? II just means that they're both the same index, which means that they're the diagonal elements. And with Einstein's notation, we just write it as MII. Alright, so an example of this, the trace of this matrix right here, let's call it M, would just be equal to 10. One thing to note, so I want to add a corollary to number 3, is that the transpose of the product of a matrix, so n times m transpose, is actually equal to m transpose times n transpose. And why? Well, quick little proof of this is, okay, well, nm transpose, let's find the elements of it, right? Split it up into its handy dandy indices. I'm telling you, you guys are gonna love index notation after this. So this, okay. Well, we know that the transpose, we flip the rows and columns, right? So this is nothing more than nmji because of the transpose. And then we also know that this is the multiplication of two matrices. And we know that the multiplication, ooh, my bad. We can write that as njk times mki, where we're using Einstein's notation. And then we can also write this as nkj transpose, right? Just flipped the rows and columns. And then this is mik transpose. And then since the elements are just numbers, I can rearrange them to look something like this. I'm just gonna reverse the order. And now look what happened. This is m transpose times n transpose, because look, the index that's summed is the outer and inner indices of both of them. So this is nothing more than m transpose n transpose ij. And that's the proof. Okay, pretty simple. One last thing I want to show is that it's a property of the trace. Even though A and B in general do not commute, it is true that the trace of A and B is equal to the trace of B and A, B times A. And why? Well, let's do a little proof again. Okay, the trace of A and B, okay, is nothing more than the sum of the elements. Remember from the diagonal elements. Remember, the trace is defined to be the sum of the diagonal elements. So this is nothing more than AB, II, okay? And since this is A times B, it's nothing more than AIJ times BJI, right? This is just matrix multiplication. On the flip side, the trace of B times A is the same thing. It's just going to be BA, II, the sum of its diagonal elements. And then again, matrix multiplication, Bij times AJI. Now notice, both of the indices are dummy. So both of the indices are dummy indices, which means that we can switch them around. We can make them whatever we want. Remember in the last video, I set it equal to alpha. The summing index could be whatever it wants. So this is nothing more than Bji times Aij. I just switched J and I, which is the same as Aij Bji, which is the same as that. Okay? Those are some little proofs for you guys. Okay, so now that we've covered these preliminaries, let us move on to the main topic of the day. And the main topic of the day is the inverse. That is our goal for today. We want to find the inverse of a matrix. How do we find it? Well, God knows. we're about to see. Alright, so you guys probably know how to find the inverse of a 2x2 matrix from Max's videos on linear algebra. If we have a matrix equation, AX equals B, then we know that the solution to this is X equals A inverse times B, right? We just multiply by A inverse on the left and A inverse on the right, and we get this equation. Okay, so in the 2x2 case, the inverse of a matrix is written as 1 over the determinant of the matrix times D negative B negative C A, where A is nothing more than A, B, C, D. So this is the general formula for the inverse of a matrix in the 2x2 case. But, and the determinant, of course, is AD minus BC. Is just the diagonal elements, you multiply them, and then you subtract the off-diagonal elements. Easy enough. How do we generalize this to the 3x3 case, though? So, how to generalize for 3x3? And then later, how will we generalize this for the n by n case? Alright, so that is our goal. And the way we're going to do this is actually a pretty stupid way, to be honest, but it's a way that a lot of work in physics is done. And it's by finding patterns, okay? And what do I mean by patterns? Well, we're gonna start off with it's called the poor man's approach. We're gonna do it using brute force method to find the inverse, and then we're gonna find a pattern from that, and then from that we're gonna generalize it to any dimension that you want. Okay, so let me show you how this is done. So let's say we have a linear system of 3 equations this time. You know what? Let me use a different color here. So we have AX plus BY plus CZ equals U. That's our first equation. And then we have DX plus EY plus FZ equals V. And what's after F? A, B, C, D, E, F, G, X plus HY plus IZ equals W. Okay, call this equation 1, equation 2, equation 3. And we want to solve this for X, Y, Z. So this is the poor man's approach. Okay, poor man's approach. I mean, I am in college, so I guess this is my approach. But don't quote me on that. Anyways, so obviously this is a 3x3 system, 3 equations, 3 unknowns. What we can do is we can eliminate one of the unknowns. We can eliminate Z. And the way we can do this is we can multiply I times equation 1, subtract that from C times equation 3. Right, to get rid of the Z. I'll multiply I by C, it's going to be ICZ, C by I, CIZ, and we're going to get rid of that. So what happens when we do that? Well, I did the math for you because I'm so generous, and what we get is this, AI minus CG times X plus BI minus CH times Y is equal to IU minus CW. Okay. Yeah. So that's one. And now, what another thing we can do is, let me pick a different color here. Another thing we can do here is do I. Oops, my bad. I times 2. Okay. Minus F times 3. So what happens when we do that? Again, we get rid of the Z. So I did the math for you once again because I'm so generous. And we get DI minus FG times X plus EI minus FH times Y equals IV minus FW. Okay. You can do this yourself. I invite you to do it so you'll be able to really learn what we're doing here. But regardless, I did the algebra for you. This is what happens. We got rid of the Z, we got rid of one of the unknowns, and now we're left with, as you can see, an equation with 2 variables. And this looks very similar to something that we had before, which is a prime x plus b prime y equals u prime, and c prime x plus d prime y equals v prime. This is just a linear equation, of a system of two linear equations. So we reduced the problem from 3 equations to 2 equations. And we know that we can write this as a prime x equals u prime, whose solution is just x equals a prime inverse times u. And we know that the inverse of a 2 by 2 matrix is just given by this formula that we had up here, right? So we basically solved this problem using the poor man's approach. Now, okay, why am I showing you this? Well, this is the main takeaway here. We were able to solve this by brute force, right? But now let's look at this determinant here. We said that the solution to this is a prime to the negative 1. And a prime to the negative 1 is nothing more than 1 over the determinant of a prime times, well, it would be d prime a prime, we flip that, and it would be negative b prime c prime. So what's the determinant of a prime? Well, what is a prime? A prime is just going to be, a prime is little a prime, little b prime, little c prime, little d prime. And we gotta match the coefficients and everything. Okay, a prime is ai minus cg, b prime is bi minus ch, c prime is di minus fg, and d prime is ei minus fh. So once you take the determinant of all that, you get whatever. All right. So that's exactly what we're gonna do in a second, and we're gonna look at it and see if we can find a pattern. Okay. So let me make a new page real quick. Do I want to save? Yes, I want to save. Let me save this as deep dive 2A. Okay. Good quality. Okay. All right. So this is exactly what we're gonna do. We are going to see what the determinant looks like. So let's say we have a matrix M for the 2 by 2 case, A, B, C, D. Determinant of M, as we all know, is just AD minus BC, right? Okay, so now watch this, watch this. This is going to be very interesting. I'm going to define some variables. So let capital A equal D, capital B equals negative C, capital C equals negative B, and capital D is equal to A. So now look at this. We can write the determinant of M like this. AA plus BB, right? A is D, so AD minus BC, right? That all checks out. But watch this. We can also write it as CC plus DD. Can we? CB, C times negative B is that, and then D times A. Ooh, okay. But we can also write this as AA plus CC, and we can also write this as BB plus DD. So you might think I'm going mad here, that I just made up these 4 random capital letters and I called it a day. But the important thing to note is that we can write the determinant in 4 ways. Okay, that's the important thing to note. And actually, what this is called, writing it these ways, is called a Laplace expansion, named after a very smart man indeed. Okay, so now I want to show you something really interesting here. Let me get a nice juicy color for this one. So, a little note. Ooh, that's so ugly. Okay, note. Note that A, B, C, D. Let's just do this real quick. Let's do this matrix multiplication here. So these are the capital letters and these are the lowercase letters. So what does that matrix multiplication give us? Well, it's going to be AA plus CC, right? AB, well, I'm running out of space here. Okay, AA plus CC, AB plus CD, right? BA plus DC, and BB plus DD. Now check this out. This is where the cool part happens. What's AA plus CC? That's just a determinant, right? And what's BB plus DD? It's just a determinant. Now what's AB plus CD? Well, capital A is just D. So this let me different color here. This term is gonna be DB, right? And then C, capital C, is nothing more than minus BD. It's 0. Okay. And then same thing here. BA is nothing more than negative AC plus AC. So that's also 0. So this thing is nothing more than determinant of, well, okay, let's call it M. Determinant of M, 0, 0, determinant of M. And I can factor out the determinant, and this is just 1, 0, 0, 1. And we all know this is just the identity matrix for a 2x2 system. Okay, so you might think, okay, this is cool, but what does this give us anything? I'm going to show you right now what this gives us. Okay, so we basically said that A, B, C, D times little a, b, c, d is equal to the determinant times the determinant of M times the identity. Okay, let me call this M star. Let me call this M equals determinant of M. Oh, I shouldn't call that M star. My bad. Actually, I could call it M star equals determinant of M times the identity. Okay, one more thing to note is that the inverse of a matrix must satisfy this. For any matrix A, the inverse of the matrix times the matrix itself has to give you the identity, right? This is a very well-known fact. If I have a number m, then its inverse is just 1 over m. 1 over m times m is just 1. Same thing for matrices. The inverse of a matrix times the matrix itself has to give you the identity. That's the definition of an inverse. So now look at this. I have a matrix times a matrix equals the identity times the determinant. So now I can do something like this. I can do 1 over determinant of m times m star, right, times m equals identity. Aha! This right here is the inverse. This is the inverse. 2 exclamation points. So we've just found the inverse of a 2x2 using this weird capital A, B, C, D. So m negative 1 is equal to 1 over determinant of m times capital A, capital B, capital C, capital D. And if you actually plug in these values, it's exactly equal to D negative B negative C A. So we've just found the matrix inverse, the inverse of the matrix, using this convoluted system where I make up A, B, C, and D. But now let's do it for the 3x3 case, and we'll see a pattern. That's the whole reason why I wanted to do this, to see this pattern. Okay? So let's do it. Let me just drag this over a bit. Okay. So 3x3 case, right? Okay. Let's see. Now our matrix M is equal to 3x3 A, B, C, D, E, F, G, H, I. Woo! That's a lot. Determinant of M, I'll just write it down for you. It's going to be equal to, we've seen it before, I just never wrote it out for you guys, but it's equal to AEI minus BDI minus AFH minus CEG plus CDH plus BFG. Okay, I think I did that right. Now, notice this. In the 2 by 2 case, we write the determinant. We write the determinant of M in 4 ways, right? We wrote it here as AA, BB, AA plus BB, CC plus DD, AA plus CC, and BB plus DD. Linear combination of the 4 variables we have. So one would suggest that in the 3 by 3 case, we can write the determinant of M in 6 ways, right? Because we now have 6 different linear combinations, okay? And that's exactly what we're going to do. So let's write the determinant of M equals AA plus BB plus CC. And let's compare. Let's compare this to that. It turns out, let's look at it. So A is going to be, well, what's the coefficients of lowercase a? It's going to be EI. Let me do this in a different color. It's going to be EI, and then here, FH. So EI minus FH. Similarly, B, capital B, is going to be, well, okay, it's going to be DI and FG, right? So negative, if you have to include the negative sign, negative DI minus FG, right? And then lastly, pick a third color here. C is going to be, it's going to be DH and EG. So DH minus EG. Okay, but now let's look a little closely here. Let's look back at our original matrix. Notice that capital A is nothing more than the determinant of, it's nothing more than the determinant of, it's nothing more than the determinant of EF and HI, right? EI minus FH. And we find A from doing this to the original matrix. So the original matrix is A, B, C, D, E, F, G, H, I. So we find A by crossing out the first row and crossing out the first column and taking the determinant of what is left. Same thing for B. Literally the same thing. We cross out, this time we're going to cross out the second column and the first row. And then we have D, I, F, G, but with a minus sign. Similarly for C, we cross out the third column, the first row, and the third column, and this is what we're left, DH minus EG. So you can see what's happening here. We find the determinant by crossing out the rows and columns with alternating signs. And this is exactly the Laplace expansion that I was talking about before. Remember over here we had, where was it? We had AA plus BB, CC plus DD. These are the Laplace expansions. And if you visualize it, it corresponds to crossing out the row and the column. Okay, and I think that's very neat. But the thing about Laplace, actually first let me do a couple of examples for you guys to make you familiar with this. So let's do this. Let's do the determinant of 2, 0, 1, 3, 1, 1, and 1, 2, 1. Okay? We Laplace expand in the first row. So what does this mean? We cross out the first column and the first row, and we take the determinant of this. The determinant of that is just 1 minus 2. So actually, let me write it out. So it's going to be 1, 1, 2, 1, right? Multiplied by 2. We need to keep this guy there too as well. Because look, A over here is multiplied by A, right? So this is the first element. B is multiplied by B here. So the same thing here we have to do. we have to keep the A. This would be the A in our previous example. We have to keep the 2, and then we take the determinant of that. Minus 0, that's the second one. And then you cross out the second row, the second column and the first row, and we did take the determinant of what's left. So it'll be the determinant of 3, 1, 1, 1. And then lastly, plus 1, which is the third one. Cross out the third column and the first row, take the determinant of what's left. 3, 1, 1, 2. And then this guy is just 0, obviously. So this is just 1 minus 2 is negative 2. 1 minus 2 is negative 1 times 2 is negative 2. And then plus 6 minus 5 plus 5 is going to be 3. Okay? In general, we can apply this to a matrix. That's a little crooked. A, B, C, D, E, F, G, H, I. Alright, so same procedure, A, and then we get rid of the first row, first column, so it's going to be E, F, H, I, minus B, and then D, F, G, I, and then plus C. We get rid of the third column in the first row, so D, E, G, H. And then if you compute this, you will see that this gives you exactly this. So we've shown that using these capital letters, they actually correspond to how we take the determinant. But the thing is there is nothing special about the first row. We were Laplace expanding in the first row, right? Because we were doing A, and then B, and then C. But there's nothing special about the first row. Watch this. This time, I'm going to do it like this. So A, B, C, D, E, F, G, H, I. We can Laplace expand, for example, in any row or column. Let me Laplace expand in the third row, for example. So this would be equal to G. I get rid of the third row, first column. I'm just left with this guy. So B, C, E, F. Then minus H, same procedure, get rid of the third row, second column. I'm left with A, C, D, F. And then plus I times A, B, D, E. And if you compute this out, it will give you the same exact thing as that. And exactly the same thing as what we had before. So there's nothing special about the first row. There's nothing special about the third row. There's nothing special about anything. And it turns out actually that what we just did right here, we can write this as this. So determinant of M is equal to G, G plus H, H plus I, I. Just as we did it here, we wrote AA plus BB plus CC, and we Laplace expanded in the first row. We do the same exact thing here. GG, HH, II. GG, and this is capital G, HH, and II. Same exact thing. That's why in the beginning I said there were 6 ways to Laplace expand to find the determinant. It's because we have a 3 by 3 matrix. Okay? And then one last thing I'm going to show you guys before we wrap this video up. Do I want to save? Yes. Deep dive 2B. Okay. Yes, I want superb quality. So I hope you guys are starting to understand the procedure to finding the determinant now. And through these examples, we're finding out the underlying structure of how the inverse works. So as I said, we can write the determinant of M as AA plus BB plus CC. And at first, this just looked like some weird crap that I decided to invent, but it turns out this is actually the Laplace expansion of the matrix. In the first row, right? Remember the matrix for this, it would be the Laplace expansion in the first row, but we can also write this as GG plus HH plus II, and this would correspond to the third row, but also we can write this as, DD plus EE plus FF. We can write it 6 different ways, right? And these are all valid ways of finding the determinant. Okay, so now, but watch this. I use a nice little pink here. Note. Just as we did in the 2x2 case, we can set this up. A, B, C, D, E, F, and G, H, I. Times A, B, C, D, E, F, G, H, I. Equals, well, okay, I'm not going to do it for you, but just trust me, you can do it if you want. You can do it if you want, but what ends up happening is you get this. Same exact thing as in the 2x2 case, just one dimension higher. You multiply the capital numbers with the lowercase numbers, and you get the determinant of m times the identity for 3x3. What this means again is that we can write this as m star m equals determinant of m times I. Whoopsie doopsie. And obviously that means that the inverse is equal to 1 over determinant of m times m star. It's very neat, right? It's very neat. And you have to give all the credit to my man, Laplace. He started off with these random capital letters. He worked with them a bit as we worked with them, and he found that they actually represent the Laplace expansion, in which you cross out the row and column, and you take the determinant of what is left. And he found that you could do this in 6 ways. And in general, for an n by n matrix, you can have n factorial ways. Okay? And we'll see that in the next video where we generalize it to n by n. But this provides the basis. We did this brute force method in the beginning where we had that system of 3 equations. We found the determinant from that by eliminating the unknown. And then we looked at this method of using the capital letters, and we found that this strange phenomenon happens where we have m star and we multiply it by m, and literally everything cancels out except for the diagonal elements. And we're just left with the determinant. And then we obviously know that m negative 1, the inverse times the matrix itself, is just the identity. So comparing this, we see that the inverse is nothing more than 1 over the determinant times this matrix here. Okay, so in the next video, we're going to take everything that we learned right here, and we're going to generalize it to an n by n matrix, and then look at an interesting way to write the inverse. It's going to be known as Cramer's rule. Okay, so I hope to see you then.